Hello, everyone. This is Anurag. I'm your instructor for CE 321, Introduction to Transportation Engineering. So this is your required transportation engineering class. I'm sure you've done CE 222, which has some introductory fun experiments for transportation engineering. This course will provide some theoretical underpinnings for that work that you did in CE 222, and then what you are going to be doing simultaneously in CE 322. So today I'm going to be talking about just the basic introduction to transportation engineering, what it is, how maybe it possibly differs from different areas of civil engineering, and then some ideas on what we'll be doing throughout the class. So I'm going to get started with the learning objectives for this lecture, which is to be able to define transportation engineering, identify the legs of transportation systems, ask the questions necessary to specify the system, and then provide examples of some performance measures. And just to be sure, a lot of things that you're going to be learning in CE 321 and in subsequent technical electives, should you be interested in transportation engineering, we'll be talking about more in depth about, for example, here we're just talking about providing examples of those performance measures, but in future classes, you'll be learning about how to actually measure those performance measures, how to actually do the computations to measure the system performance, for example. Okay. So, and I'm also specifying, as I'm going through this lecture, I'm also specifying the section and subsections of the textbook where you might find this material. If you don't find this material on the precise subsections, just look around it and you will be able to find, what is the definition of transportation engineering, for example, in the textbook nearby these sections. So goal of transportation engineering is the safe and efficient movement of people and goods. I've underlined safe and efficient. Both goals are critical. Obviously, safety comes first. So we want to have people be as safe as possible, but then we have to balance that with the efficiency requirement. Now, obviously, if we are to move everybody at a very, very small speeds, that would be fairly safe, but we cannot always achieve that. So we try to achieve the most safe speed that we can achieve while still providing the efficient movement, and then there is a balance of that, and then that balance shifts between the context of the transportation systems. For example, on an urban downtown streets, you don't necessarily want people moving very fast. You want people to be moving slowly, have an environment where pedestrians and bicyclists and cars potentially, and transit can potentially move together. So there would have to be a slower speed. We don't care as much about efficiency there. We probably shouldn't. But once you're on the highway system where there's nothing for miles, maybe you want people to be able to move faster. So you design interstate highway type systems. So safe and efficient movement, the balance shifts between what type of system you're talking about. And the other thing about transportation system is that, we apply the physical and the hard sciences. A lot of that will be talked about in the transportation design part, pavement design part, where there is a lot of physics, applications of physics, a lot of applications of material sciences, for example. And then we have also the soft sciences, because you will see human beings sort of interacting with the system, right? So there is a lot of human factors type issues, a lot of social issues that are important for transportation engineering. So in that way, transportation engineering is a little bit different than other branches of civil engineering, because it has that soft sciences combination as well. Social sciences, human factors, psychology, all of those things. We have to be aware of that. We have to be knowledgeable about that to be able to do transportation engineering. And that may or may not be the case in that is sometimes is not the case to the same extent in other branches of civil engineering. Demand for transportation engineering is derived demand. And that's sort of another characteristic of of transportation engineering because most of the travel is to a destination. People travel for work, people travel for sightseeing. People have, sometimes we just take road trips, a scenic road trip for the sake of it, but those are very few and far between. For the most part, our demand is, a derived demand. You don't necessarily want to visit zip code 93407, for anything. You come here, and if you identify that's the Cal Poly zip code, as a student of Cal Poly, you come here to attend classes and so forth. So every trip has a purpose, and the demand for travel is based on that purpose. So we always call transportation demand to be a derived demand. And for the most part, all the planning, all the design, all the operations that we look for or that we analyze is based on this idea that transportation demand is in fact derived demand. Okay, so when we're trying to learn about transportation systems, it requires knowledge of three major areas. First of those is components. What are the transportation system components? Here, I would advise you to pause the video for a minute and think about what those components might be. Now that you've had a chance to think about what those components might be, if you thought about vehicles, if you thought about roads, if you thought about sort of parking areas, if you thought about airport terminals, those are basically the components of the transportation systems. And obviously, these components are designed by different engineers, different planners. For example, when you're thinking about vehicles, those are primarily, especially the personal automobiles, those are primarily designed by private automobile companies. But then if you're talking about the system itself, the roads, those are designed by the transportation engineer at your local agency or at your state highway system and so forth. And then leg two would be the activities involved in putting the system in place. So this is where, we are most interested in. This is what you're going to be learning in this class, and then even in your technical elective, should you choose to do emphasis in transportation engineering in your career. So this is what we are training you for, activities involved in putting the systems in place. And those broadly can be sort of broken down in terms of planning of the system, designing of the system, and construction, and then design and construction. And then the third one would be sort of operational analysis. Once the system is in place, how do you analyze it? How do you make sure that it's performing to the extent that it can, and so forth. And then our leg three would be issues that may not be included in the decision-making process, but are affected by the decision. Now, this is sort of your, externalities. Those are sort of your cost. For example, for the longest time, we didn't think a lot about noise pollution or the particulate emissions and the smog and things like that come from vehicular transportation. And those are the things that we started addressing after the fact. So those were sort of considered leg three. But the newest trend, I think, what is happening in the transportation engineering profession, and which is a welcome trend, it is that now you're trying to account for those issues, those leg three issues in leg two. And that sort of brings me to my next point, like thinking about accessibility, for example, accessibility for disabled individuals, where would that fall under? How about safety of the transportation system, right? So initially, what we thought about the accessibility piece was that this was something of a leg three issue. We used to think about that after the fact, after we built the interstate highway system, we built a lot of our transportation system in this country, and then we thought about accessibility once the Americans for Disability Act was passed in the 1990s, late 1980s through 1990s, when these issues became more prominent. We started thinking about those issues. So this was sort of something that we did after the fact, right? So this was sort of thought of as a leg three issue, but that's not the case anymore. We're more and more emphasizing that we have to take care of these issues at the outset, at the at the beginning of the system. And same thing about safety, although it's a little bit critical, a little bit more of a challenging issue. You'll learn more about that a little bit later in this class, but then also you'll learn about that if you were to take an advanced level technical in transportation safety, is that we used to obviously account for safety in our transportation systems, but the way we used to do that is by adhering to the standards, right? For example, we used to account for the fact that the force that you'll require to stay on a curved path, we always made sure that your radius of that curve was appropriate, that you could travel at that design speed on that curve. So we always did that. So that was always a leg 2 issue, So we always thought about safety in those terms, and we call that the nominal safety terms. We always accounted for that as a leg 2 issue. However, even if you sort of make your systems nominally safe, that does not mean that you're never going to have any collisions or crashes on your system, right? Because people are interacting with the system. So your goal is to create a system where collisions are less likely to happen. And this was something we treated that as an after the fact issue by maybe providing some signage and things like that. But I think now, with the advent of Highway Safety Manual that came out only in 2010, now we're talking about estimating the number of crashes at the planning stages as well. So we are doing that now more and more. So safety, we call it substantive safety, in trying to figure out how many crashes can we expect on that facility, beforehand. Even if we always meet the standards, right? There are going to be some crashes, and recognition of that fact and sort of trying to minimize those crashes at the design and planning level is happening more and more. So that used to be a leg 3 issue, again, becoming more of a leg 2 issue now. So we're trying to sort of account for those leg 3 issues now in our activities that we are. So that's why, that we are undertaking. And so that's why the issue, the role of transportation engineer in the society has been evolving quite a bit. Our profession is evolving quite a bit as well. So this is a very interesting time to be in this profession. So transportation system analysis, that's what a lot of you would be doing. We have a full course on that as well, especially from an economics perspective. That's CE 528 that you might be interested in the future. But it's a way to design and modify the system to meet the use of end users. So this is what we have to keep in mind, and their behavior, their expectations, all of that comes into play as well. So some of the questions that we have to answer is that if that system even feasible from a cost perspective, and then what are going to be the cost? If it's a feasible system, what is the range of the cost at the beginning of the planning level? We sort of make a rough estimate of the cost, perhaps with a higher sort of standard deviation estimate, where we get a range of the cost. But then once we go closer to the bidding, when we're trying to put the system in place, we have to come up with the cost that is more sort of precise estimate of the cost. That's a very, very narrow estimate, right? So that we can get an idea about what the bid ought to be for a project. And then are there any alternatives? What alternatives could we consider? A lot of engineering economics analysis that you're going to learn in the class is about picking alternatives in terms of benefits and costs and so forth. So we try to estimate the end user benefits and compare them to cost. And then we can, based on those costs and benefits, we can pick out which alternatives suit us the best in terms of what we should be putting in place. So all of those details you're going to learn in part of that in this class, but then if you're interested in future technical electives as well. But here I'm just giving you a brief overview of what you're going to be, just setting the context of what you're going to be learning in this class. So a very important thing for a transportation engineer, transportation planner, is to be able to ask the right question. And those questions, those contexts determine what we are going to be end up doing. And those involve purpose of the system, what is the system for? And I was talking about, sort of the difference between an urban, urban street in an urban downtown area versus a rural area where there's nothing in between for miles. Those two systems serve quite a different purpose. And then depending upon that, you design the system completely differently. Area of coverage. If you're designing a transit system, is it a regional transit system? Is it a transit system for a city? Is it a transit system for a university, for example? Cal Poly has a sprawling campus, and you have classes all over the place. We don't allow skateboards, for example, as of right now on this campus. So people have to get to the class. Are there, what type of area of coverage we might need for a system that's designed to have, some of the campuses are experimenting with automated people movers. And then that's a pretty interesting thing. And you can sort of think about, all of these questions. What will be a very interesting exercise for you all would be to think about automated people mover implemented potentially at our campus at Cal Poly, and then, ask these questions of yourself and try to answer those questions to the best of your abilities at this point. So you'll get an idea about, what kind of exercises it takes. Now, obviously, you're not going to be able to answer all those questions precisely, but it'll be a very valuable exercise for you to think about the role of the transportation system planner and system designer as to what type of challenges that they have to face. And those are a good way of deciding whether or not you're interested in that subject area. Are those challenges are something that excite you? So you'll have to think about technical specification. You'll have to think about how many people does it need to move. And when you're thinking about capacity, you have to think about, if it's a very successful system, it might create its own demand, right? If we can move people faster, maybe we can enroll more people, or maybe people will take more classes, maybe the gap between classes, instead of being 10 minutes, maybe it will reduce to 7 minutes, for example, now because we have an efficient people mover system. Maybe in the long run, we can offer more classes, whatever it is, right? Reliability of the system. How reliable does that system have to be? What would be the failure rate and cost effectiveness? Would that be a cost effective system that Cal Poly can actually run, or would that be too cost prohibitive? So I would be interested for you to think about an automated people mover system for the context of Cal Poly State University, our campus in San Luis Obispo. And what do these questions look like for that kind of a system? Okay. And then lastly, I want to talk a little bit about what we're going to spend a lot of time in this class and in the future classes, is that anytime there is a system, and we have to think about performance measures. And some of the examples of performance measures could be average speed. What is the range of the area that it can serve? The cost of operation is a very important performance measure. Can you run the system at a lower cost? What is the reliability? It's a very important performance measure. Again, how many failures can you expect? For example, when we design our roadway system, for example, we design it for the 30th highest hour of the year, and that means that we are designed for how much traffic would you expect on a yearly basis, the 30th highest hour. We don't design it for the highest possible hour in the year. So for example, we don't design the system, a roadway system or a signal or whatever it is, for the highest amount of traffic that we'll see in an hour over a year. No, we don't design it for the worst hour. We design it for the 30th worst hour. So we expect the system to fail or people to face congestion for 29 hours of the year. There is a sort of evolution of the transportation system that's happening that contends that in the urban areas, because we design it for cars to move for the most part, even that 30th hour is a way over designed, because for the remaining hours of the days, it encourages fast amount of travel because we provide high number of lanes, we provide wider lanes, and so forth. So even there is an evolution happening that is saying even that 30th hour is too much. So failures, what I want to talk about here, what I want to mention here is that the failure is not necessarily, obviously failure in terms of collision is pretty bad, but in terms of congestion, sometimes, we do allow for some failure because we want to have a system that functions more effectively, and we're not always way over designing in terms of, congestion should never occur. We plan for some congestion would occur, and, potentially we are okay with that in general. So that's what I'm saying, like, transportation engineering is a little bit different than than other profession. Here, in terms of congestion, we expect some failure even when we're designing. So for example, even with the prevailing design philosophy, we allow for failures for the 30 hours of the year because we design it for the 30th worst hour of traffic over the year-long period. And even that philosophy, as I said, is evolving now to be, maybe we shouldn't design it for even the 30th hour, because that still might be a little bit of an over design that leads to higher speed and less safe operations during other hours of the year. So these are interesting things that we'll talk about again in the future, but I just wanted to give you a flavor of that. Okay, with that, I will conclude this lecture. If you have any questions, please reach out to me. I'm Anurag Pandey, Professor of Civil Engineering here at Cal Poly, and I have listed my phone number and my email, which is the best way to reach me. But if you want to set up an appointment to meet outside of my office hours, you can use that using the Calendly link. And then I'll make sure that these slides and a recording of these slides are available to you on your PolyLearn. Again, if you have any questions whatsoever, never hesitate to ask. I always say that only bad questions are the ones that you don't ask. So always ask any questions that you might have. With that, I will conclude my lecture and stop sharing the screen. And again, thank you so much. Thank you so much, and I will see you around.